case they miss it, they can always watch the first half of the video. Okay, we're in lecture 2, and like I promised, I'm super excited to talk about Van Emde Boas trees.
How do you pronounce that?
Van Emde Boas, I guess. Maybe, yeah. Van Emde Boas trees. So, like, the slight story behind it is that, actually, okay, the slight story behind it is that this wasn't actually. The slight story behind this data structure is that, okay, like, I know, okay, this is the guy's name, right? So, like, Van Emde Boas. And the Boas, you can Google it. But the data structure isn't just by him alone. So you can imagine, like, for example, trees usually, like, if there's someone's name on it, like, you know, like that guy came up with it, right? But, like, the unfortunate story was an entire team actually came up with this data structure because they had this very important question which I'm about to pose to you guys. So I find it kind of unfortunate that none of the team members' names are on it except for his. Because, like, I've been reading up on data structure literature recently for my FIP, and, like, a lot of people really like this because they think it was this, like, wow, you know, like, holy shit, you could actually, like, do a lot more and with, like, the data structure that he made, and, you know, everyone goes, oh, this guy's amazing data structure, and then, you know, like, the team doesn't get mentioned as often, which is, like, very sad. Can you imagine him just going around going, hi, let's all make this data structure, and then, like, he stamps his name on it? That's pretty sad. And anyway, let me give you the motivation first for why this data structure was very interesting and why, like, it was sort of like the first of its kind when people were talking about it. And I'll also tell you right now off the bat that this guy is actually used like in your house. Like chances are it's really used every day, every second in your house. So what am I talking about? I'm talking about network routers. So if you have a router, right, and a packet comes in, okay, like, or maybe it's going out, let's say, right? So what's the job of the router in your house? What does it do? Great. Yes. So how does it do the routing? How does it do the routing?
Routing table.
Okay, great. So there's a routing table. Could you like sort of like slightly describe how that works?
So we have like which subnet goes to which IP kind of thing. Then from there it's like it searches out which port to send to, or then just send it to the internet or something.
So right now I'm not too concerned about the ports. But let's talk about like the IP portion. Right, so usually you have like some set of rules, right? Like it will tell you, okay, if like for example my packet comes in and it's like of like whatever, like, you know, like maybe it fulfills like the first however many bits, I should follow the rules, right? And the intuition is that the idea is that in the table, if you have a more specific rule that the IP like follows, you should be using that rule, right? So for like, you know, I've drawn up this example here, and let's say my packet comes in and it has like, again, I could be like slightly inaccurate, but I'm pretty sure this is how the idea of how it works. Again, I'm not from networks, so correct me if I'm wrong. But you know, if I had a packet that was like, let's say all zeros here, which rule should I be following? Like, let's say these were my rules. Which rule should I? Sorry?
First one.
The first one, right? Because it doesn't fulfill any of the other rules, right? Okay, so let's say I make this 1110. Oh wait, I duplicated this. Oops, 11. Let's say 00. Okay, and let's say now it came in like this, 01. Which one do I follow? Second one, right? It doesn't fulfill this guy. This is too specific, but and it's more. This guy is more specific. This rule is more specific than this guy because I fulfill more bits, right? So I should really be following this guy. Make sense? So I know it seems unrelated, but right now the idea for incoming packets is that when I have them come in bits, I really want to find the rule that again, like, you know, is the closest to what I have. Okay. Now, what if I told you this was very similar to trying to find predecessors in a set? Can you see how that would be related? So what I mean by that is, let's say I have a set S. Okay, it's just a collection of numbers right now. Okay, so like it could be like, let's say like any number X, where like X needs like is between I don't know 0 and 2 to the power of 32 minus 1. Right? And right now I can support like insert, lookup, and everything, let's say pretty quickly for now, and we'll get into the specifics of that later on, but I also have the predecessor operation. So what the predecessor operation does is that if I give it a value t, okay, it needs to output an x such that x is in the set, okay, and x is the largest number smaller than or equals to t. Yes. Can you see how that would help me here? Seems unrelated, right? But why does this work? easy, just shut it off.
You just change all the question marks to zeros and you just put all those 4 numbers inside your set and you just call the predecessor
Can
function.
use a different color. So, right, so the idea is, like for example, this guy is a rule, right? What I'll do is that I'll insert 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, like 0, 0, 0, 0. Like insert all these guys into my set and think of them as numbers, not as a sequence of bits. Okay, so when my new packet comes in and it comes in with something like this, I should interpret it as a number, and if I get the predecessor, right, whatever the predecessor is in this set is actually the rule that I can, the most specific rule that I can follow. Does that make sense? Okay, like you guys don't look very convinced, but it's great, right? Okay, so why is this great? Because your routers need to be fast, right? Okay, and the whole point is when under Boas trees does this. Like, okay, like let me talk about how fast this is. So if there's a small caveat, but let's say I had 32 bits. If I need 32 bits to describe all the integers that come in, right, and everything in my set, okay, I'm going, like the guarantee is that I should be able to do it on the order of log base, like log 32, roughly.
Side question. What's the 1101, right? The predecessor will be the 1100, right?
Yeah, I was thinking of that.
Say again, so 110.
The third one, the predecessor is the third one, right? No, sorry, 101.
If you insert a row, that's all ones, all the way until the last 4 bit, you can change it to 1100, then the row selector will be that one.
Right, so then you want the opposite, right? You should fill it with ones instead, I think. Or you can do like successor. The successor help you here.
I think there's something, the rules probably don't match entirely or something, I don't know.
No, as in like, okay, so should you change it to ones instead? Let's see. What happens if you change it to ones? 1, 1, 1, 1, and you look for successor instead. Does that help you?
I think that's the one. So
If you look for the successor, then you'll find the fourth one.
1, 1, 1, 1, 1, 1, 1. Or is it zeros? Uh-oh. Let's see.
I think it's the issue with the
Right?
I think it's the issue with the rules. I think the rules,
The rules kind of like overlap or something.
yeah.
Oh, they can't overlap, right? Can
They're not supposed to overlap.
Yeah, they're not supposed to overlap. Oops. Oops. Okay. Sorry, again, not a networks person, but that's kind of actually roughly the idea. I'm pretty sure it's supposed to work somehow. Okay, wait, I'll work out on those details later, but basically that's the rough idea. Okay, and let's say that I could represent all my integers like using 32 bits. Okay, I actually only need roughly like really close to log base 2 of 32 operations, right? Which would be what, 5 operations, which is actually pretty great for a router. You don't want to use hashing or you don't want to go through everything to try to find the rules, because routers are supposed to be fast. They're supposed to push your packets through as fast as they can, right? Like if you're playing a game, for example, or if you're watching videos, you don't really want it to take all this time to go through your entire set, go through a hash table, go through a linked list, or even go through a tree, right? So let me give a quick motivation, like and a quick comparison as to why these things work well, or like why they are preferred over standard trees. So let's say I had n rules for now. Orange. So let's say I had n rules for now, or like n items in my set basically. Okay, like let's say like I haven't told you about Van Boas trees. What's the best data structure you can come up with that does insert, lookup, delete, and let's say predecessor really quickly? Okay, let's say AVL trees or like any balanced binary search tree, right? So if I use the BBST, right? So I mean I do get insert, I do get delete, I do get lookup, and I do get successor or predecessor. Right? What's the time complexity if I add items? Log n, right? Great. So with a small caveat like I mentioned, let's say I assumed that my items came from a set view. So I'm trying to be a bit specific here. If let's say I also had the assumption plus the assumption that my items came from some universe. So I'm going to call the set U so that each item in the universe only needs let's say, log u bits to represent. Okay. Oh, actually, no, I shouldn't use u here, that would be bad. Let's say log n bits. Okay. My guarantee to you by the end of the day is that I can do all these things in log n time. Seems wacky, right? And the cool thing is that in this case, right, let's say m was polynomial in n. Let's say m was equals to n. It's not really true, but let's say m was like, polynomial in n. Wait, I actually don't need log n bits, sorry. M bits. This is my guarantee actually. So again, if you're using, let's say IPv4, you have 32 bits, right? I can do it in log 32, like roughly. And if you have like 64 bits for IPv6, right? 64 bits, 128, right? So if you have 128, like the eyeball, like ballpark figure is like log of 128, which is what, log of 7, right? Log of 7 is, sorry, log of 2 to the power 7, so that's log of 7. Okay? Yeah. Right? So it's really, really small. It's a really, really small number. But you need this assumption. Okay? So let me explain why before I go on. This doesn't mean that this works for everything, alright? This assumption is very critical. The reason is that if you were to do anything fast, like for example, let's just talk about like insert and delete and lookup, maybe successor as well. But if you do these things really quickly, you actually break like a sorting overall. Because let's say the reason why binary search trees work, if you don't remember, is that you're doing comparisons only, and you don't care about like whether they can be represented by bits or whether they come from some universe, right? So when you're doing general comparisons, this is really the best you can do. Okay, and that's very important. So when you ask yourself the question, can I do better? And when the answer turns out you can, don't forget it comes with a very big caveat here. Without this assumption, and in general, you can only do this much, right? If you've taken 3230, you should like roughly remember why. It's because you can't do comparison-based sorts too quickly. If you haven't seen it yet, you should probably see it this semester in case you're taking it already. If not, come by and ask me a question. Okay, so let's begin. The roadmap for today. Wait, any questions before I begin?
So basically it means it's a constant element inside the set universe.
The constant element inside the set universe. No, what I mean actually is more like, let's say I only need m bits to represent any item in the universe. I have roughly 2 to the m items in my universe, right?
It's bounded by m.
Yeah. Okay, yeah. So, wait, m bits, m items? Yeah. Okay, so let's see. Let's begin. The roadmap for today, or how I hope to finish this, or like start and finish this, is that I'm going to give you a simple solution first to an easy problem. Okay? And then what we're going to do is that solution isn't going to work very well. In fact, all of you are going to be very familiar with it. I'm going to apply some recursion. We'll do a bit of divide and conquer. And then what we're going to do is that there's going to be a lot of bugs. And the last portion of the talk is going to be me us squashing all the bugs. And by the time we're done squashing all the bugs, you get this really, really amazing data structure. So like I think up to this point, it will look like a really, really amazing data structure, except it's not really fast. And then like around this point, we start going, yeah, okay, let's actually like go handle the details, and then everything works out fine. Okay. And bonus, if we have time, I really want to cover 2 independent hashing today, if we have time, so that if I can push a topic earlier on, I can cover more like in the second half of the semester. Okay, so let's begin. So let's say for now, let's make it very easy. Let's make it really, really easy. So my universe has m items. Okay, now I only want to do 3 things fast. Just 3 things, forget about the rest for now. Okay, I want to do insert fast, I want to do delete fast, okay, I want to do lookup fast. Okay, so again, assume that you have like your universe is like of like m items. So that means, right, that whatever you have to deal with, whatever items come in, right, it's one of these m items only. Nothing outside of that. Okay? I want you to be able to insert this, like design a data structure that if I do insert, right, I want this to run in O1 time. If I want to do delete, I want it to run in O1 time. If I want to do lookup, I want you to do it in O1 time. So again, the usual like, okay, given x, and I'm promised that x is one of the m items. Okay, like I should be able to insert it in O1 time, or delete or lookup. What's the first thing you can think of? Hash tables. Okay. I have something faster than a hash table, because my concern, and again, this is the reason why I want to talk about 2 independent hashing, is because it's a great solution in expectation, and I can like eventually show you that it works very, very well. But let's say I want a really good guarantee, and I don't even want like, let's say like, oh, it's probably very good. I want it to always be good, no matter what. Okay, an array, sure, like sounds pretty funny, right? Like why use an array? But how would you do the array? Exactly. So what's the size of your array?
Size of the unit.
Exactly. So what you do is, the first iteration of this, the Van Boas tree, starts from the humble beginnings of just using an array. I'm serious. I'm really serious. Okay, so basically, right, what you're gonna do is you're gonna maintain an array of size m. Okay, and exactly like you mentioned, each item is a it's going to be represented using a unique index on this array. Okay, so let's say I want to insert. So okay, fine. So I guess you kind of have the idea, but I need to start out the data structure with like some initialized values, right? Before I do anything else. So what should the array have?
Like minus some like sentiment and value.
Sure. So let's say I don't know, false maybe, just to say that it's like fresh, right?
Yeah.
Okay. So let's say I want to insert item item 1. What should I do? Okay, so one where I can't add one everywhere.
To the specific element.
Exactly, right? So like for example, let's say this was like that index, the corresponding index, right? What you do is maybe you'll say, okay, it's in the set, I set it to true. Okay, great. So let's say now I also want to, okay, maybe I'll add 2 more, maybe 2 and 3 as well. So let's say 2 and 3. Okay, now let's say I want to do delete. That's simple as well, right? Okay, so I won't insult you by like testing whether you guys know that. Let's say I want to delete 1, instead of being true, you simply set it back to false. Okay, but this isn't great unless I also know how to do lookup. So how would I do lookup? Let's say I want to do lookup of 1. What should I be doing?
Check the slope.
Check. Exactly. Just check the bit, right? So this array really just tells you, hey, it's an item in the set. And since you're guaranteed that you only have m elements, you don't have to worry about them asking questions that are beyond your capability. Right? That's the promise that we're given. Right? Okay, so this would be great and we can all go home and have fun if you weren't for the fact that we also need to do successor. Alright, so I have an array, size m, right? Size m. Now let's say I've done some inserts, I've done some deletes. Some of these are true, maybe this one is false, maybe this one is true, so on and so forth. What's the worst case time for successor? How would I do successor now? Let's say I don't make any more changes to the data structure.
Linear time.
Why linear?
Just check 1 by 1.
Exactly, right? So like and you don't know, that's kind of the issue, right? So like in the worst case, you could probably have like a decent chunk of these that are all empty, right? And maybe like somewhere a third of the way down the road, that's where the next true guy, that's where the next item is that's present. And let's say I did a successor like early on in the array, right? Assuming I don't know anything else, like it's pretty difficult to see like we could speed it up. You probably have to go through the entire thing, right? So when we say linear here, it's not ON, the number of items, it's actually like OM, the size of the universe. That's really bad, right? Okay, so this is actually the end of chapter 1. It's kind of like us saying, okay, this is crap. Like an array is fast for insert, delete, and lookup, but we really don't have successor, and we really want successor, right? And if we didn't have successor, again, like this, either this works or a hash table works, right? But we really want successor so that all of us can like play computer games and like watch videos. So let's work on that. So what was the huge caveat? What was the huge caveat of using just a simple array? Okay, so like, what do you mean by no ordering?
So from the index you can tell nothing about.
Okay, so from the index you can't tell nothing, right? So I'm going to be drawing many straight lines today. But I need a really big one. Okay, so yeah, wow, right? Okay, well maybe not like that, but for now let's just see it looks like this, right? Again, the caveat is that when I want a successor, I kind of have to travel really far down the array because I don't know where the next guy is going to be, right? So let me bring you to chapter 2. I actually didn't write that down, but let me bring you to chapter 2. So the question becomes this. Let's say that I had a way of like peeking ahead somehow. And let me tell you how I'm going to do that. What I'm going to do is I'm going to cut my array of size m. I'm not going to actually cut it, okay? But I'm just going to say that I'm going to subdivide it into segments of size root m. So this is segment 1, we call it cluster, so this is cluster 1, this is going to be of size root m, this is cluster 2, it's going to be of size root m, so on and so forth. Okay, now if I keep dividing up my array like this, right, and each cluster is of size root m, how many clusters do I have? Root m, great, okay, so I have root m clusters. Now for each of these clusters, I'm going to dedicate a single bit to it, somewhere else, separately. Okay, so cluster 1 gets a bit for itself, that's good. Cluster 2 gets a bit for itself, that's good. And since there's root m clusters, I only need an extra root m bits on the side. Okay, so all of these guys I'll keep in one more array. So this is the main array, and this is going to be let's say the summary array. I don't really want to spoil it, but now you have an array of size m, you have an array of size root m. my question is, let's say I give you this. Do you think you could try to perhaps speed up successor a bit more? How?
Another array.
Yeah, the summary will contain whether that segment has a true in it.
Okay, so for example, let's say this guy was all empty. Let's say this guy has like 1. Let me draw a box here, right? And maybe all zeros. Maybe this guy also has like 2, or like maybe a lot of 1s. I said 2 and then I drew too many. And maybe let's say this guy has 1, 1. Okay, so as per your suggestion, I'm guessing what you're trying to say is that there should be a 1 here. This should be 0 if it's all empty. This guy should have a 1. This guy should have a 1. How would you run successor now? Let's say I wanted a successor of this item here.
I just check the next segment, which
Okay.
has. So I will check inside the thing first.
Okay.
And then afterwards, I will check the summary to see where's the next one. Then I will check inside the segment to find the next one.
Great. So let me see if I got your idea correctly. What you do is, let's say I wanted the successor of this item here. What I'm going to do is I'm going to start from this segment first, and I won't start behind it. I'll start in front of it, and I'll look for this entire segment, like as in like the portion after it, and see whether there's a 1. Okay. So let's say there was a 1 in a good case. On a good day, there was a 1. How long does it take for me to go through the entire thing? Root M, right? Okay, great. Except for the fact that maybe what you're looking for isn't in the cluster, right? So what you should be doing is you should be looking for the next non-empty cluster, right? It saves you time, right? Because then you don't have to go through the process of going through really, really empty clusters. So fine, so what you do is, okay, I'll go up, and then I'll find the next non-empty cluster, right? But how many of these boxes do you have to go through? Root M, right? Root M, great. So after that, you find the next guy, and then you go, okay, I found the next non-empty cluster, so you're guaranteed that there's some element in the cluster. Make sense? Right? So then you start from the beginning, and then you do the same thing, right? But this guy is also of size root M. So in total, you actually only have to check like root M, 3 root M elements, like indices, right? So now that just based on this simple structure and with an extra root M space, which is you're already using M, root M is nothing, right? You can do successor in like on the order of O root M time. Okay. I don't really want to say you can right now because we still have to maintain the other operations. It'd be bad if I do this fast and the rest slow, right? So before we move on, let me ask, like, how long will it take for us to do insertion? Or how should we do insertion?
We just all the bits or something.
Okay, so we all the bits, right? So let's say this cluster was empty and now I want to insert an item into it. What do I do?
That's all.
So if I insert, do I have to all everything?
No, all the specific one and summary array.
Great. So if I plug in an item here, it doesn't matter if the array is full anymore. I don't have to check anything in the array. I know it's full. I'm just going to set the summary bit to 1 for this cluster. Okay, make sense? Lookup should still be easy. I don't have to do anything with the summary array. I just have to touch the original guy itself. Okay. One last question. Delete. Root M. Okay, like
Can you keep a size of each summary?
I was going to set that as a question for your assignment, but
Okay.
thanks, you spelled it. But yes, you can. One slow way, if you really don't want extra space, is you just go through the entire thing. That's going to take real time, right? But the other way is you just keep a count. When the count hits 0, you know that there's nothing else left inside, and you should just automatically set this guy to 0, right? Now I have to come up with new questions. I was like, no, like maybe like if I don't post that question, people won't ask, and then I won't tell, and then so we keep these time complexities for now. Okay, so chapter 2 is pretty much done. Congrats, you're like halfway there. Sorry?
What was his question?
Okay, so his question was, so my question basically was, let's say I had to delete from a cluster. I still need to maintain the summary bit.
Okay.
How well can I do it? I mean, of course, an easy solution would be root M. When you delete, you're not sure, you just check through the entire thing, right? His proposed solution, which actually works, is that if you could sacrifice just a little bit more space, just save a counter. Right? And if you save a counter, when it hits 0, there's nothing in there, so you should set it back to 0. Then, since you keep maintaining this structure along with your other array, this takes root time. Hello. Okay. Make sure you don't stand in front of the camera. Okay, so we still have these. That's great. Now we're gonna move on. So you're pretty much done with roughly, I would say 35 to 40% of the data structure. Pretty cool, huh? It took years for them to figure it out, and it takes you like 30 minutes to pick it up. Can you imagine how sad like it would be if you spent like years on something and then you would just go, yeah, I got it in 30 minutes. Okay, that's not actually true, because like when you're trying to find something, it's actually a lot more difficult than once you know the solution. I don't know, just random ramblings. Okay, so now we have this idea. this is the part where we start doing recursion. And I think it's really cool because we always do recursion on algorithms, and I've never seen recursion on data structures. So it's really amazing. So what I'm going to do is I'm going to try to repeat this square root decomposition idea. I'm not going to do it at one level. I'm not going to do it at two. I'm actually going to keep doing it until I can't. So what I mean by that is that let's make this data structure. Let's call it V for now. Okay. Now V, I'm going to define it recursively. Okay. It's going to contain. Wait, I should be more specific. So I'm going to say this data structure works for a universe of size M. Okay. So that's how I parameterize it. Let me know if it's not clear at the end of like after this. Actually, I should leave it on the side so that I have space to draw more arrays later on. So I'm going to define a data structure V on a universe of size M. Okay, it's going to contain a few things. It's going to contain how many? Okay, I need root M many V of root M's. So I'll call those clusters using this guy. I'll draw it out later. Let me just define it now first. Okay, and I need one more, like one summary structure, which is this guy. So in other words, what my Van der Waals tree, like not really a Van der Waals tree, what my pseudo Van der Waals tree right now looks like this. So if this was V of M, okay, basically what it will contain is another V of M, another V of root M, right? This guy is the summary. And I'm going to contain another root M many V of root M's. Oh, okay, I shouldn't draw that many, I'm kind of lazy. So let me just
V again.
So this is the proposed data structure right now. I'm defining it recursively.
Oh, okay.
Okay. So there's going to be 1, 2. How many do I need? I need root M many. And each of these are a V of root M. So in other words, these are actually the same data structure, but on a smaller universe. Okay? Let's not worry about space for now. I really want to push the idea through. Is everyone following me? Great. Okay. So let's say we had this, right? Right now, I want to go through the whole process of defining insert, delete, and lookup again. And this time is really important because after that, we're going to see where all the bugs are and we're going to squash them. Okay? So let's actually like properly and like actually do this. So I actually do have to write down the pseudocode or write down whatever code you guys give me. So let's try to doing insertion right now. And remember, we have to do it recursively because it's a recursive data structure right now. Make sense? Okay, so let's do insert. So let's say I want to insert an item X. Okay, what should I be doing?
Insert the correct sum data structure.
Okay, so in this case, let's say X came from root M many. So I need to figure out which are the correct clusters, right? So which class? Let's say I did a canonical ordering. So like this is like from 1 to root M. This is from root M to 2 root M. This is from 3 root M to like 4 root M, and so on and so forth until the last root M. So I have a number X that comes in. Which cluster should I, let's say for now, like X divided by root M, right? So what I'm going to do is I'm going to insert into X divided by root M's cluster. But there's a small caveat. I don't really insert X. What should I actually be inserting? Let me do it in a slightly easier way. Let's say my classes right now are all size 3, and I want to insert item number 5. Which cluster do I pick? Like, how do I tell which cluster do I pick?
The quotient.
Oh, you guys use quotient? Okay. So the cluster you pick is actually, in this case, if my clusters were of size 3, I would, like an item was, let's say X, I would have to pick the X divided by 3. That sounds weird. The X divided by 3 cluster, right? In that case, it would be the second cluster. But what number do I insert in this guy? I don't insert the old number, right? Like 5 is actually the second item in this cluster. How do I find that number? It's the mod. It's the quotient, right? So what I insert is actually I should use a different color. One second, I can't even fill my marker. Okay. So what I do is I'm going to insert X mod square root of M into the X over root M cluster. Again, these are details. I'm pretty sure you can work them out. So I hope you don't get confused right now. Okay. So great. But do I only do this insertion? That's not exactly great. I mean, like, sure, it stores the item, but what else do I need to do?
Update the summary array.
Exactly, update the summary array, right? So by updating the summary array, since this is actually by itself a v of root m. Okay, what I'll do is I'm going to insert. What do I insert? What number do I insert?
X over.
Exactly. The x over root m. Like insert this number into the summary. Right? So again, in case you didn't follow, I have an item x. Okay, I need to do two things right now. I need to update the summary. Okay, I do that by figuring out which cluster it is first, right? Let's say, so to figure out which cluster it is, again, I get this number, right? I should be inserting that cluster, so I will recurse from that. Okay, and then what I'm going to say is that since this cluster is now not empty, I'm going to have to also update the summary. And in actual fact, what I'm doing is I'm going to insert this number into the summary. This isn't like the full algorithm, by the way, like for Emde Boas trees, but it's a start, right? It's recursive. I mean, I hope you can handle the base cases. Okay, so let's not do that. Okay, so for now, this is our insert. If you're fast, you actually realize that this is actually already too slow. But let's move on and cover finish up the algorithms before we do the analysis. Let's do delete. Okay, so how should I be doing delete? Now this one is a bit of a difficult. Sorry?
Can I clarify what are you inserting to summary?
You're inserting this number.
The number itself. So, okay.
Right? Because you know, can you imagine this data structure has a promise? The promise is that when you call insert, you give it a number and it does that. Right? So in the case of insert, what we're going to say is, okay, I need to do two things. I need to pick out the correct cluster to insert, and from that cluster, I will insert x mod root m, and then on the summary itself, I will insert x over root m. You're inserting two numbers.
Why x mod m?
Okay, so let me draw the thing magically. Okay.
Are we talking about bits like just now?
No, these are numbers, right? But you can represent them with bits.
Okay.
Right? So let's say your clusters were of size 3, let's just say. And I want to insert number 5. Right? Which cluster should I pick? The second one, how do you decide that?
Over
5 over 3, right? Okay, but I can't go to this cluster itself and say I'm going to insert 5. That doesn't make sense. I'm out of its universe.
Okay.
Right? So it's between like what, like 4, 5, and 6 in your outer view, right? But amongst it itself, what value are you actually? The second value, right? So how do you get that value? It's 5, like it's mod 3. Okay. Right? So that's how you get this number. That's how you get this number.
So the item you're inserting is actually kind of like the index of
Yes.
Okay.
Yes.
Maybe I can make one clarification. I think it's important for you to know that M represents the size of your universe. Okay? So when you look at each of the cluster, you don't want M to be big. Does that make sense? So if my original universe is 1,000,000, I'm dividing them into 1,000. I don't want the V of root M to also be representing very big set. I only want them to represent 1,000. And so the numbers that I can insert can only lie from 0 to 1,000, right? So that's the reason, okay, when you look at that root M, it is not just a number, it also tells you what is the size that you can insert, okay? And this thing about doing the mod is just like shifting. When you do, okay, I don't know, in operating system, when you do virtual memory, okay, instead of having this, we break it into blocks, and then after that, you just look at the index within the block, okay? And that's really what they're doing. It's not a very difficult idea, okay? We do that all the time anyway, okay? All right, but the important thing is to note that when you go down, as you recurse down, the blocks get smaller and smaller, so you're representing smaller and smaller set. The numbers you can insert are much smaller, okay?
Okay, great. Thanks.
I think I was confused just now with the summary thing. Just now when you're discussing the basic one, just now the part 1, summary was basically a true or false array, right?
Sorry, the
In the summary, when we discussed previously before this one,
Yes.
when we were discussing the simple solution, summary was basically a true or false, right?
Yes.
Discussed.
Yes.
So in this case, you mean insert x over root, are you literally throwing the number into the correct index?
Yes. So you're not going into the you're going to the index and saying true ostensibly.
Okay.
Make sense?
Yeah.
You can actually change it to a number like to count instead, but let's not deal with those details right now.
Yeah.
Okay. So let's do delete. Okay. Now delete is a little bit more involved, slightly. So let's say I want to do delete. What's the first thing I should definitely be doing?
Check resistance.
Okay. Let's say you always promise it exists. I mean, we'll do lookup in a bit, like in a bit. But yeah, let's say okay. So let's say I'm done with this. Okay. And now you want to do like now you actually want to remove the item. What should you do?
Same thing as insert.
Exactly. Like Close, close. There's a bit more. Close.
Start with the first one.
Yes, yes, right. So what you do is you want to find the responsible cluster and you want to remove it from that cluster. Make sense? Because that's where it sits, right? So you know, again, you find the correct cluster and then you delete that item, right? So you basically delete x mod root m from x over root m cluster. This part is all fine and dandy, but like there's kind of an issue, right? What happens to the summary? Okay, so you kind of not only need a successor function right now, you also need the predecessor function to see whether it's empty, right? Because the caveat here is really that when you're deleting, again, you don't know whether this cluster is going to be empty after you're done with it. So then now you have to have a fast way of figuring out whether it's empty, and then you have to, you know, if it's empty, you have to delete from the summary again, right? So there's kind of an issue. It's like the idea itself is great if you just use predecessor and successor to find out whether the cluster is empty after you're done with deletion. That actually makes sense. But I argue there's a faster way.
Use only successor?
No, not even use successor.
Use a summary.
Not using a summary array. Sorry? Yeah, exactly. Use a counter, right? Store a counter at every count. Oh my god, I forgot. Use a counter here, use a counter here, and so on and so forth. Right? When you've done deletion on the cluster, you know it's empty. You go, I'm done. I kind of need to update the summary array, right? And what do I need to do? Yeah, in terms of updating the summary array, what should I actually be doing?
If it's empty, set to false.
If it's empty, you set it to false. By setting it to false, I mean you delete this like, for example, this is the second cluster. You delete 2 from the summary data structure. Right? Okay. So I won't go through the counter details, but if the cluster is now empty, okay, delete the value x over root m from summary. Okay, let me just mention, right, that like the predecessor and successor idea was actually also how I started out doing it. But the issue is that when you look at the time complexity analysis data, you realize that that's really, really way too slow. In some sense, like I think it does slow it down. Or if not, it's still the same. But this is a
quick question for the summary array. Can't you like combine the summary and the size counter array into a single one?
No, but you want a separate counter for each data structure.
He's asking store the counter inside the summary array instead of the.
Oh yeah, sure. That's fine. I mean, like, you know, if it works, it works. Right?
Then if you have a counter, then the summary array is like not much issue.
Oh yeah, I mean, okay, fine. Well, if you had the counter and you know it's non-zero, you can sort of use that idea. But I want this structure because this guy is also going to be fast at the end of the day.
Oh yeah.
Right.
So if you use a counter and you're just saying that you're storing an array of counters, that probably won't work very well because I actually do want this guy to be fast later on as well.
Right.
Make sense? Okay. Okay, great. Good questions. Let's do lookup. Should be fine, right? How do I do lookup? I hope I don't have to code that one for you guys. How do I do lookup? Giggles like, oh, such a silly question.
Yeah, the first line from insert, then just change sort insert.
Code golfing. Okay, yeah, I mean the idea is pretty much that if I want to look for an item, I just need to find the cluster that it's responsible for and then just recurse on that guy. So that's fine. Lookup is going to be none of our issues today. Okay, so let me okay, one more, successor. So successor still pretty much works the same way. How do I do successor?
Yes, right. Call successor the same first line.
Okay.
Then there's nothing to call successor somewhere, then call successor on here.
Okay, great. Right, so again, the idea is pretty much the same. I have not really changed much of the code, much of the idea. All I've done is actually really just replace the arrays with the recursive version of it. Right, the algorithms are still pretty much the same. Right, the idea again is what you're going to do is you're going to just find successor of x mod root m in the x over root mth cluster. Funny thing, by the way, like I realized that this number gets repeated a lot. So I think in CLRS they got very sick of doing that. So they actually like, oh, we defined this to be like some funny symbol, so they could save their time writing this. If it exists, we return it. Okay. Else, what we do is we find successor of what do we find it on this guy in summary, and then we get the minimum. Okay, wait, I kind of need to, let's say, call it call it, let's say alpha, find minimum element in alpha cluster. That's the general idea. Again, like this is going to be pretty slow actually, so we're actually going to speed it up. Okay, are we clear on this right now? Again, this is still too slow, and I'm going to show you why it's too slow. If not, we could be done, and like I would be pretty happy. In fact, the first time I learned this, I stopped here and I was like, oh, we have it. Then I bounded it and I was like, oh no, we don't have it.
Is it like root m slow or slower?
It's log m slow actually. Now log m sounds amazing, but log m is crap for us. It's exponentially slower than what I'm promising you. It's pretty sad. I'm giving you log m, so log m is like, you might as well use the binary search tree, right? Okay, so let's start with insert. Time complexity analysis. I'm supposed to, like, you know, if I were to eyeball it, I would actually do it the 3230 way and I'll save you like 5 minutes, but I found I spent a lot of time trying to do it like without assuming 3230 knowledge, so indulge me. but okay, so the time it takes for insert. So how many recursive calls am I doing? Over here. Two. In the worst case, I do 2. Maybe you can optimize it by just doing 1, right? But it's unavoidable based on my algorithm right now. I have to do 2, right? And even if you say, okay, I'm going to store a counter so I know when I have to do it, the first time you insert, you're still screwed. You still have to do it twice. Make sense? Okay. So T, like my running time on T on my universe of size M right now, I need to do 2 calls. How on size what? Root M, exactly. Okay. And for each level of recursion, I actually only do O1 work. I'm not doing anything special on every level of recursion. Make sense? So this is O1. Okay. So if I were to draw the amount of work as a tree, right? I'm basically, I have a problem of size M. I'm going to break it into 2 portions. Each portion of size M over 2. I'll just do one more level. When you break it again, you're going to be like you're going to be working on problem sizes of M over 4, M over 4. M over 4, so on and so forth, until when the recursion tree stops. Okay? Sorry? Oh yeah, root M. Oh my god, old habits die hard. We always do 2. Thanks. Okay, great.
So the second will be 4th root, right?
I swear I've never drawn this recursion tree in my life. Okay, for slight convenience, you can actually stop whenever the recursion tree, like the size of the problem is actually constant. And I'll have technical issues if I stop when the problem size is 1. So take it for granted that I'm going to stop when the problem size is 2. If the problem size is 2, this is easy. You don't even need a Van Boas tree anymore. It's just in the real size 2. That's fine, right? Okay. So again, like I always ask my 2040S students, when you want to bound a recursion tree like this, there are 2 important questions you need to ask yourself. What's the first important question? Okay, what's the height of the tree? So in this case, that's the harder question actually. But what's the height of this tree? I start with M, and at every level, I'm going to apply a root on it. Yeah, okay, fine, that's pretty fast. But so how you get it, remember, I stop when it's 2, right? So I'm doing 1 over 2 to the power of, let's say, the number of levels, let's call that L, right? And then this is 2, right? So if I do 1 log, that brings it down to this, right? And then I do, okay, let me shift it around a bit, but this guy is actually just 1, so this is equals to 1 over 2 to the L. Did I do it correctly? Come on, I missed something out. Log M. That was pretty important, right? Now I shift this guy out here again. This gives me 2 to the L is log M, right? Which means that L is log M. Oh look, it's the shape that I promised you. But there's a small issue.
Either that you are with 2 to the power L equals to M. You can instantly see it.
I shouldn't see it that way, but I actually did all this. okay, but whatever works, right? Okay, so I showed you the height of the tree is log M. And like some of you have correctly pointed out, the key issue here is that even though this is exactly what I want to give you, I don't have that right now. The issue is that the amount of work you do per level actually doubles per level of recursion. Okay, and in this case, it's actually worse at the bottom. I mean, if you sum everything up, I don't really want to do that because it's a geometric progression and like it has a lot of ugly terms and I'll probably put you guys to sleep. But the idea is that the amount of work you do here, let's just say we take the lowest like work at the leaves. How much work is there? It's 2 to the log M. At the very least. In fact, actually at most. Like I can put a 2 in here and it'll actually bound the entire tree. Okay, but it's on the order of 2 to the log n, which actually just gives me log n. Oh, I like we don't have the promise. Not yet, at least, not yet. Okay, so there's still a ways to go, but we're kind of heading in the right direction. The interesting thing here that I find is that when you move past the square root decomposition and you keep recursing on it, you can even push root m down to log n. I think that's pretty cool. Okay, but this is insert, right? Delete will work very similarly. If you have to do 2 recursive calls, you do end up getting this time complexity. Okay, and for successor, you kind of need, I think, you need at least 2 calls. And you want to find the minimum. Okay, you can store the minimum, and we'll talk about that later. But at the very least, these things right now are far from log n, right? So we kind of need to improve that. And I think I should point out that the crux of the issue with all this in the analysis is that this guy, we don't want to do 2 recursive calls. That's really way too expensive. We don't have enough time. And we if we can just kill this guy, make only 1 recursive call, we're done. Okay, right? Because let me just quickly, I don't have to quickly do it, but as in I don't have to do it. It's not that I don't have to quickly do it, but if let's say instead my running time complexity was this, then we're in good shape. This is log n. For the same reasons, except you don't double your working at every level. Make sense? Okay. So really, what we're really done with the recursion portion and the simple solution. Now we get to squashing the bugs. Okay. And let me see, which one should I start with? Okay, let me quickly fix this. Let me quickly fix this before we actually start squashing the actual bugs. But successor right now, I make 1 call here and I make 1 call here, and I still need to find the minimum. That's kind of bad. That's kind of bad if I have to go through everything, right? So let me say straight up right off the bat that what you can do is that for every cluster you store the minimum as well. So finding this guy takes O1 time. Okay. I don't really want to write it in the code because if I write it in the code, I have to write it here. It's in my notes and I'll publish it. But for now, that's not a huge issue. I hope. Okay. So okay, we have these three algorithms. Now we're going to squash the bugs. Which one do I start with? I don't remember. I start with. Okay, screw it. Let's start with insert. So insert right now has 2 recursive calls. That's kind of an issue. Does anyone have any suggestions on how I'm going to cut it down to just 1 call? You don't have to think too hard, but yeah. And we're going to go through multiple iterations. We're actually going to go back and forth. But what's the issue here? Why am I making 2 calls?
You need the summary array.
Okay, I need the summary array. But do I always need to update into the summary?
Not really.
Not really. So when do I update into the summary?
When there's nothing there.
When there's nothing there, right? So what we mean by that is that if I had all these clusters, right, and it's my first time inserting, let's say into this cluster and it's empty, okay, then by my algorithm right now, I don't really have a choice. I kind of have to insert into the cluster and then again into the summary. That's bad, right? So this is a bit of a trick, and I think some of you have seen it before, but it's not very, I don't think it's very common, or at least in my circles it's not very common. How can I cut this down to just 1 level of recursion? Sounds like a riddle, huh? It's like one of those, yeah, how can he be here and there at the same time? But
Bit masking.
bit masking? What do you mean by bit masking?
Actually no. Still accept that. Never mind.
It's fine, it's fine. The whole point is trying. It'll be very weird. But I think it's a really cool trick, and you'll see more of it in the coming weeks. How do I cut it down to 1 level of recursion? Just doing 1 recursive call.
Is it something like the Karatsuba kind of thing? I don't know.
I mean, it's in that spirit. You want to cut down the recursive calls. But it's a really cheap trick. It sounds very buzzwordy. It's like, watch him cut down the time complexity with this one weird trick. But I really want you guys to get it.
But do you have to do 2 at one point, but then for the rest of the
Fractional
time
cascading.
What's fractional cascading?
Not sure, it's like something.
Huh? Sorry?
I don't know. Okay, I think you can describe your it's like quite difficult to describe. It's like you have multiple arrays, then you want to speed up.
No, you don't need anything that smart. In fact, I would argue that again, we're going to go through the idea of doing less work actually saves you, doing work a bit lazily actually gets you what you want. Surprisingly. I'll give you one more hint. It's really unavoidable. You have to insert into the summary. You don't have a choice. Like, I'll tell you that much. Because if later on let's say after you did that insertion into an empty cluster and someone wants to do a successor and you are the successor, that summary cluster better say that your cluster is an empty.
It's a lazy propagation.
Yeah. Okay.
Can you say it again?
So again, well, I'm not revealing the solution, but I'll give you a hint of the two recursive calls, right? It has to be spent on the summary. The reason why it has to be spent on the summary is because if let's say you inserted something, it was the first item in this cluster, okay? And let's say the operation after that was a successor operation and you were the successor. Okay, so like maybe you inserted something here and like after that when someone called a successor here, you are actually the next item. Right? The summary better say that this cluster is not empty. You don't want to be overlooked in that search. Okay, well, at least that's like the motivating. I mean, maybe you could make it work, but like we're going with this idea. Okay, so you have to spend that one recursive call here. You can't make any more recursive calls at this level of recursion. You can't go into the data structure anymore. What can you do?
So update early when you get successor.
Not exactly. Not exactly. If you're from CS3233, this should be like your favorite two words.
Store the number directly.
Yeah, store the number directly, exactly like you mentioned, lazy propagation. So what you do is you don't actually recurse on it. You really keep it there. You really keep it there, right? So actually, like this is getting a bit out of hand, but I kind of like do need to mention that right now I'm not only going to keep these items. So this is like one of the two things that these are two of the things that I need. But I need a third thing. I need a minimum. Okay, and what I'm gonna do is that when I'm inserting into that guy, okay, if it's empty, right, I don't recurse, I just set the minimum to that item. Okay, so in other words, so right now my data structure also has a minimum, and if let's say this entire guy was empty and I'm inserting something into it, I don't insert, I just set the minimum to that item. It doesn't go anywhere further down the tree. Okay, that's the idea. Are we clear on this? It might feel a bit weird, but again, like this really saves you the time. Okay? And again, this falls in line with what you want with successor. And if you want to do, the insert, I don't really want to change the code here, it's in my notes, but that's how it works. And let's say I want to do delete, again, the idea is that this is the only item, you don't even have to recurse anymore, just check it. Okay? Or you could also recurse, but we're gonna fix that. Okay, so are we clear on this? Like, this doesn't fix everything, but it kind of somewhat fixes it. Okay? So I've cut it down to one level of recursion, one recursive call if I'm inserting into an empty data structure. I still need to deal with the other cases, right? So what other cases are there? So if I'm inserting into an empty data structure, okay, my algorithm is I'm just going to set, let's say inserting x, I'm just going to set min of that data structure to be x, right? But what other cases are there? Okay, when it's not empty, then what should I do? Like how many other cases are there? It's a few. We actually have to squash all of them.
It's either empty or non-empty.
Okay. So let's say inserting the new x is less than the current min. Okay. So this is case 1, this is case 2. If it's less than min, what should I be doing?
Update the min.
Okay, I update min. What do I do after that? Push what down?
Push the original min.
Exactly, push the old min down, right? Okay, now I have a question here. How many recursive calls am I doing in this case? At worst 2? That would be bad, right?
Yeah.
Okay, but I argue it's actually not 2, it's actually still 1.
Lazy again.
Because they are lazy.
Lazy, right? So what you do is when there's an item that's smaller than the minimum, right? You set the, like for example, let's say item A comes into this data structure and it's smaller than the minimum. I set that minimum to this guy and I don't push him down anymore. I push x down into the recursion instead. And since I know that this data structure originally contained at least one minimum item, do I have to update the summary structure? No, right? So that's fine. Make sense? Okay, great. So we push out min. Now the next question is, what happens if x is larger than the minimum?
Keep the minimum and push x.
Exactly, right? So what you do is, why did you say push? Thanks. Like recursively insert. So recursively insert, right? So likewise over here, what you just do is you just repeat whatever you're doing, you recursively insert x. And again, you don't have to touch the summary data structure because it had some item, the summary structure is okay. Make sense? Okay? So we've kind of like fixed insert. There's actually going to be a lot more we need to tack onto it. Not now though, because right now, like in our view, it's actually totally okay. So let's talk about delete. Okay, so what's the issue with delete? What's the issue with delete? Okay, so yeah, there are a few more cases now. Let's say that I want to delete an item and if x was the minimum. That's actually the difficult case. let's say x right now isn't the minimum. We still repeat the same process, right? Okay. Let's say x was the minimum. What do we do?
Call the successor the minimum.
Okay, if you call successor, it's going to be a bit too slow. Because you need to do what, like one level of recursion or something, and then you need to kind of like pull that item out, and if you have no guarantee that you can do it quickly, you're still going to go two calls. You can make it one call. In fact, you can find the next item in one time. You can find the next item in one time. So if what I mean by that is that this is a data structure, okay, and you want to delete the minimum item. You have to find the next item. That's fine. Like how you do it in a binary search tree or anything. Let's say I'm deleting the minimum. Some guy needs to replace it. I need to update this guy. Right? I argue you can find the next item one time. It's pretty mind blowing when I figured it out. Link them together, that'd be too expensive. Like what if you like
Link this idea. Link
This
this
you just
idea.
go down by one level.
do I go down? Okay, what do I do?
Speak first.
Because it's a recursive structure, that means if there's some other minimum that's like even smaller, then it should have been put down further. So
Okay.
you just need to go down one level.
Sort of, but you still have to be precise about where you're going down or what you're looking
Link
at.
list.
Why is a question?
Because that requires extra pointers and stuff, and if I actually want to, one of the extra topics that I was going to give you guys is XPath and YPath tries. You can't use linked list idea because it'd be too expensive.
No, mine is a question. Is the mean here is the mean of the whole tree?
Yes, of this tree. So like this guy
So
has
it's not
his own.
each cluster, right?
Yeah. I mean, no, as in like, yeah. So yeah.
So it's mean of the whole thing.
Yeah. So like for example, this guy here also has his own version because it's defined, etc. Right? But this guy itself, he has one.
Okay.
Okay. I'll give you a hint. Remember how we did insert? Min is never in any of these guys.
Or just delete.
It's not inside, right? Okay. So if, as in the issue is that you can delete it. You can just move this guy away. But the concern is if I have another item in the clusters, that guy needs to be the new minimum.
Check the min of that cluster.
Check the min of which cluster?
Of the old of this min.
But this guy isn't in any of the clusters. That's the hint.
Find the mean of the x divided by.
So I want you to find the guy after this. I mean, ostensibly using successor, right? But I don't need the successor call. I don't really want to do a successor call.
There's only one min throughout the entire
Check
line.
the min.
This min is the min across all of them. Each of them have their own recursive role.
Oh, okay.
So again, the hint is right. This guy sits here. He's not in any of the clusters.
Check the mean of the x divided by root n first.
X divided by root m cluster. Sure.
Oh, yeah,
But what if that's
this one,
empty? What if that's empty? It could be empty, right?
Then you check the next one.
Oh, we're going back to root m time. I repeat the hint. The hint is really subtle. The hint is right. X is not in any of these guys.
So the successor of x should be like the leftmost min of those clusters.
So how do you get that in O1 time?
Summary array.
Yes. Okay, what do you do the summary array? Close. Okay, what does the min of the summary array give you?
The next cluster.
What do you mean by next cluster?
The next cluster is one. And then you
And then?
find the min of that cluster.
Exactly. You guys get it? You guys? Okay, like yeah. Okay. Again, do you get it? Okay, so again, the idea, remember, x, right, is stored here. You like by how our insertion algorithm works. I don't ever put x down into the clusters. So whatever's in the clusters, right, are actually items that were not the minimum. They went down, right? Okay. So if let's say x wasn't the minimum, like if let's say I want to find the guy that's like after x, he's the smallest smallest guy that actually went down, right? So the smallest guy that went down, where should I find him? He should be in like the earliest cluster that's not empty. How do I find that? Well, this guy stores a minimum. Let me pull him out. That guy tells me the first cluster that's not empty, right? Go to that cluster. Which item am I looking for?
Depends on their summary array.
Or
the mean, or the mean.
It's the mean, yes. Wait, are you guys following? Because we're not following it, let me know.
Yes.
I'll give you guys like a bit of time.
What does the summary array store?
Right? So these all things like this, like all of these things are like one tree. Like they're all collected together.
What does the summary array
Yeah, the summary array is again the same thing, right? It's like again this thing but like smaller. So it has its own version of minimum as well.
Oh, okay.
Remember? So like this guy is like one tree and then you recurse so then it gives you another one.
Wait, how do you find the earliest cluster that is non-empty?
So this guy is his own data structure, the same data structure, so he has his own minimum, right?
Yeah.
So what happens if, so what is this guy's minimum? It's
Oh, okay.
the minimum element of this guy.
So summary is on the
This guy is his own tree.
I see.
Does that make sense?
Yeah, you should clarify.
So I know which cluster is contains content.
You should say that because all the other things
I
are
kept
very
saying it.
Right? So I go
Yes.
into that cluster.
How again? I don't really.
So again, remember the idea is that these guys are their own like version of the same data structure but recursed,
Yeah.
right? So I mean like recursion is pretty trippy and like what doing on a data structure is like even weirder. But this guy is his own like okay, it's not a VB tree yet, it's a VB tree. You know, this guy has his own VB tree, this guy has his own VB tree, and so on and so forth. So this guy has his own minimum, this guy has his own minimum, this guy has his own minimum. This entire thing I have like my own minimum as well.
Maybe you use an example of actual numbers.
Okay.
Easier for people to see.
Kind of reminds me of this time like Prof Ma like in linear algebra like said like, oh, to all you theory students, please read the examples because if not you can't do the computations in the final exam. I didn't listen to his advice, so guess how well I felt on the computation questions. Not very well. Okay, so let's say maybe the min here is 5, and I don't know, let's say the next item after that is 7, and 7 is stored in this cluster. Right? Again, the min 5, this is his own VB tree, this is his own VB tree, this is his own VB tree, so on and so forth. Right? I want to find the item after 5, and let's say in that case it's 7, right? So everything here is empty, like as in like this item doesn't sit, this item here doesn't sit. Okay, thanks Prof, bye Prof. These are all empty, right? Right? Shading is empty. Okay, if I want to find the next item after 5, I'm looking for the first non-empty cluster, right? So in that case, right, this guy, the cluster, like, okay, this is 1, this is 2, and this is 3, right? 1 is not in the set, 2 is in the set, right? Because this is the first non-empty cluster. Does that make sense?
Oh.
Okay. So if I say, okay, after 5, what's the next guy that is after me? So it's like the smallest guy in the earliest cluster, right? So I go to the summary and say, you know, what's your earliest cluster? Oh, the earliest cluster is 2, so you go, okay, so minimum is 2, so I go to the second cluster and I go, what's your minimum item? Because this guy also stores his own minimum, which points to 7. Then I pull 7 out. I see more nodding of heads. So can we give up success? Okay? These are actually, okay, in this case this is an actual number.
So by right that is
By right should be
7
like over root m, yeah.
7 mod root.
Just think of 7 as stored in a set and this is the cluster that's responsible for it right now. Does that help you? Well, I mean, if you question it then I'll just have to like divide by root m. I mean not like, sorry, 7 mod root m.
You take the ball as in
Okay?
Wait, the 2 is the summary.
has its own mean.
Yeah, because it's its own data structure.
Does
So
it
like,
mean that if I already have a mean x? Oh wait, but it's not inside the one of the array. That's why the summary. Okay, I see.
okay?
Yeah, I see.
Okay. Again, recursion, like don't go through like the levels and mix everything up. That's like O1S like student, you know, like and we always go, don't you know like your students always go like, oh but then if I go down here and then go down, then you're like, no, stop doing the recursion, you're not supposed to do the recursion. And right behind that, every time I teach ready for DS, it's like, oh stop doing the recursion, then they're like stack overflow and stuff. Okay, like but that's the idea, right? So again, like I cannot emphasize enough. This guy is his own VB tree. This guy is his own VB tree. This guy is his own VB tree. They're all their own VB tree. They have their own minimums. They have their own like sets to deal with. Make sense? Okay, so again, let me reiterate. If I want to find the guy after 5, right, it's the earliest null-empty cluster, it's the earliest item in the earliest null-empty cluster. So I go to this guy, I pull out the minimum, that's free. Then I go to this guy and I pull out the minimum, that's free. I mean, it's not free, it's O1, but O1 is free. Right? Okay. I mean, in our world, like constants like are cheap. Okay, so that's the idea. So if you want to do deletion, and I'm deleting the minimum element. Okay. So what I do is I find out where the next item is. Okay. So that I tell my VB tree, okay, this current item not supposed to be you anymore, right? If there is one guy after me, what should I be doing? What should I be doing? I need to update this guy. So I go with the idea, I find the minimum and then find the minimum, I set it to that, right? So maybe the new minimum is x prime. But I'm not exactly done.
Delete x prime.
Exactly. What you want, you have to remove it. You have to remove it because I don't want the minimum sitting over here. Right now it's not an issue. Right now everything is fine, right? But we're gonna see in a bit. If I keep the minimum inside, it's gonna eat a lot of time. Okay. Actually no, I think we'll see it very soon. I mean like yeah, really soon. So fine. So let's say I deleted the minimum. Let's say I updated the minimum, then I have to go into the cluster and then delete this guy. Okay. So then you like for example, let's say the next guy was here, x prime. You go into that cluster and you go, okay, I'm deleting you. Then you like what you're actually intuitively doing is you're just pulling inside zoop up here. So again, you never recursively store the minimum. It's always stored somewhere like further up, like lazy propagation or whatever, like you want to call it. Okay. So okay, what cases have we dealt with? For deletion, we've dealt with the case where we want to delete the minimum. Okay. Now let's say I want to delete something that's larger than the minimum. What do I do? Delete just because on the cluster, right? That's also free. That's fine, right? I also have like one other issue. My other issue right now is wait, hold on. Let me just like x larger than minimum is kind of taken care of. My other issue right now is what happens if I'm deleting the empty Venom the Boas tree. Sorry, yeah, last element. What am I doing? Yeah. So like if you're deleting like this thing is empty and there's still a like a non-zero minimum, right? Like a null minimum. You just literally turn that guy off, but you're not done. What else you have to do? Upwards. What upwards? Not exactly upwards, but there's something here that further upwards exactly the summary, right? So this guy now is empty. Like in case the guy further up is like screwed, you kind of need to delete from the summary. But that's fine, right? Because deleting from this, like clearing out this guy is free. You set the minimum to null. Make sense? Okay. So great. We kind of have insertion and deletion. Like that's roughly the idea. Let's do successor because we've not paid attention to it in a while. So let's do successor. So successor now. Again, we had how many calls? We had 2 calls, right? Okay, we had 2 calls. So the first call was to say, I'll look in the cluster, I'll call successor on that cluster, okay, and then if it's in that cluster, well, good. We stop with one recursive call. That's great, right? That's my promise to you. But in the worst case, it's not. Then you kind of have an issue. So what should you do? How do you fix this, right? Because if it's not, right? For example, I guess I'll draw a picture. Reminds me of like this math prof that always does proof by pictures. It's very weird. Okay, so let's say my item was here, and I want to find successor, and there's nothing after it, right? Then we went through the whole process, right? If I find successor here, let's say there's nothing after x. I called successor, there's nothing there. Then I need to call successor on this guy, and then call successor on the corresponding cluster. That's a bit too slow. That's really way too slow, right? How do I speed it up? Compare with minimum. I want successor, right? So if I'm larger than minimum, it doesn't say anything. But you're on the right track. On the right track.
It's smaller than the minimum, just return the minimum.
Okay, if it's smaller than minimum, you return the minimum.
Larger than minimum, you query the specific cluster.
This still doesn't help you, right? Because if let's say the minimum was here, the minimum isn't really there. The minimum is here, right? If it's smaller than minimum, yes, I agree. You return the minimum value. Yeah. If it's larger than minimum, you're not sure. Right? So like, let's say I zoom in on this guy and consider all the items. Maybe the minimum here and x is here. I still don't know like whether this is in.
Use the summary array.
Use the summary array? Okay, how would you use summary array again? Okay, what if like there were items here as well? The new summary array will point you here.
Another field in the summary array.
Okay, what would you store in the field of summary array? Good sir? You had a suggestion? Yeah, I thought you had a suggestion. Did you?
Start the maximum.
Exactly, store the maximum. Why store the minimum only? Getting lonely. Let's store the maximum. Okay, what happens if you store the maximum? What can you do?
So you could exactly like pinpoint the question mark there.
Uh-huh.
Whether
Exactly.
or not-
So you see, if I asked the predecessor question, right, your answer would have been spot on. Right? Because if I want the predecessor, I check if it's smaller than the minimum, then I can save that up, right? Okay, great. So let's say I had the maximum. Let's say I had the maximum, right? What you do is you check your current value against the maximum. If you're smaller than the maximum, the successor has to be in your cluster. Okay? If you're larger than the maximum, your exactly next cluster, right? So what do? You go to the successor, you call successor on the summary data structure, then you find the minimum of that item, right? Like in that cluster. Right? Okay? One recursive call. That's great. Okay? But there's kind of a small issue now. We fixed successor, but bugs have actually cropped up in the other algorithms.
Oh no.
I mean, it's not like Java will give you a compile error, but usually your algorithm will just run really, really slowly, and I think that's an even worse bug. Because at least if it's a compile error, the running time of your algorithm is all 0. Right? Okay, so bugs have cropped up, and I don't really want to point them out this time. Let me see if you guys can catch them. So where have the bugs cropped up now? And I'll tell you it's a running time issue.
By adding maximum record.
Yeah, because remember, like successor was slow, because if the minimum doesn't help me. I mean, it could in some cases.
Like when you're doing lazy, you need push both min and max downwards. So like 2.
Something like that. Along those lines, you're kind of like getting there. But let me reiterate. So the issue is that we needed maximum for successor to be fast. Okay, and of course you're going to need minimum for predecessor to be fast, right? So again, let me quickly mention the idea is that when you want the successor of an item, you compare it with the max of that cluster. If you're smaller than the maximum, you know it's in that cluster, you just find successor in that, you're done. If it's larger than the maximum, you know it's not in that cluster, you can spend your recursive call on the summary instead. Whatever it gives you, whatever cluster it gives you, you take the minimum. So you're down to one recursive call. Successor is now successfully long time. Okay, I didn't mean to, yeah. But the issue is that now we're storing the maximum, right? It's like there's like some issue with insert lookup, insert and delete now. What issue could that be? I have a small feeling that maybe you guys made the advanced step and then like assume that it did something, and so like everything actually works out fine. And then in my view, I'm assuming that you guys did the naive thing, which actually leads to the slower runtime.
You have to be lazy with the max also.
Exactly, you have to be lazy with the max also. What happens if you're not lazy with the max?
Then you will not have your glorious log n.
Okay, why wouldn't I have my like glorious log n?
So you are doing two operations.
When would you do two operations?
Doing the insert.
During the first insert in the cluster.
Okay, doing the first insert and doing the last delete in the cluster.
Yeah.
Right? So in case you didn't catch that, the issue is that if let's say I did also recursively like I don't know why I say install, but like let's say you're recursively trying to insert the maximum, right? The first time you do it and you're going to insert, if it's the first item and you say, oh, it's the maximum, I'm going to insert it, again you run into the issue of having to update both the summary and the cluster. That's two recursive calls. You don't want that. Okay? So store the max, not recursively. Lazily store it in the current level. Okay? Likewise, for delete, right, the issue is kind of, if let's say you had some minimum item and some maximum item, and you deleted the items in between, eventually let's say the min is going to become the max. And if the max is stored downwards and you delete the max, right, you're going to have to also delete from the summary. Again, that's an issue. We only want one recursive call. Okay? So the full idea, the algorithm is pretty much the same for min and max, right? You don't want to store them, you want to keep them exactly where they are, as in you don't want to move them down. Okay? So my last question is this. Let's say I'm deleting the max. And so let's say min is strictly like less than max, and it's like, I don't know, maybe there's some items in between. So like there's some items, and then there's like min, and there's max in your data structure. Okay? We've dealt with how to delete minimum. How do I delete maximum? Which item is it? You should be able to answer this by now. But it's like, I'm not trying to pressure you guys, but like, which item is it?
One right before the next. Then you take out.
Okay, Okay, yeah, but
Then
where?
if it's a minimum, then there will be a problem.
Is it,
Summary array.
okay, go to the summary array. I want the item just before the maximum.
Look
Is it,
backwards.
Find
Sorry?
max.
Look backwards.
okay, look back. What do you mean by look
Max
backwards,
of
right?
summary array.
Okay, the max of the summary array, what does that
And
give
then
me?
you retrieve the max.
Exactly, right? So like how when we deleted the minimum, we need to find the next guy, and we did that by saying the minimum of the summary is the first non-empty cluster, and the minimum of that guy is the first guy larger than min. Likewise, right, the largest cluster, right, the latest cluster, the largest element in that is like the first element just before the maximum. Okay, then what you do is you go to the summary, say, okay, give me your max, and then after you take the max, you go to that cluster, and you take that, and you delete that max, and you send it to your new guy. Okay, I mean there's like the other case which is, oh, what if it's only min and max, but then you don't have to do any recursion, you just set one to the other if you're trying to delete it, like it should be well. Okay, like those are the rough ideas. But and like again, I sketched this in full detail in the notes. But congrats, you have a Venom Boas tree. Fast, right? Why you guys so today? 6:18. Okay, I still have, let's say like roughly 30 minutes left actually. Wait, oh yeah, questions. I forgot. Questions.
Break, yeah.
Oh, you want break? Oh yeah. I forgot that you guys probably want to like pee and stuff. So like 10 minutes. 10 minutes.
When do they learn segment trees?
Next week.